All right, welcome to our third lecture in this course on algebraic topology. We're here at the University of New South Wales, and I'm Norman Wildberger. So last time we were talking about one-dimensional topology, and we introduced the idea of a group structure on a circle, purely geometrically. And today I just want to start by saying a few more things about the one-dimensional case. So a little bit more about the circle and other connections. And then we're going to move to two-dimensional surfaces. And we're going to look at the sphere in a number of different ways. And we'll make contact with quite a few interesting areas of mathematics. All right, so one thing that we can do with the group structure on the circle is we can use it to define those maps that wrapped around the circle. So here's a circle, and there's our origin, which is the identity for this group. And I remind you that if you take an element A and you want to square it, then what you do is you take the tangent and then you make a parallel line through the origin rather, and then this point here is A squared. So this is a squaring map on the circle defined purely algebraically, or purely geometrically rather. And if we want to relate that to angles, well then it's not too hard to see that these angles are exactly the same. We're just doubling the angle in the obvious way. All right, so this is then a way for us to define a function. So we can define a function, let's call it, say, gamma, from the circle to the circle by defining gamma of A to be A squared. So that what happens then is that if we visualize this in terms of two copies of the circle, if A is over here, there's the origin in both cases. If A is over here, then A squared will be up here somewhere. And so as the A goes all the way around, so the gamma of A over here will go around twice, because the angle is twice in every case. So gamma of A wraps around twice. And it's defined purely in terms of the group structure. Because it's twice, we could maybe put a subscript 2 under there, suggesting that we could do the same thing for other integers. More generally, we could define gamma sub n from the circle to the circle by defining gamma of n of A to be A to the n. And that's valid for, well, let me just say what that means. So it means A times A times A all the way n times if n is bigger than or equal to 0. And if n is negative, let's say n is equal to minus k, then it would mean A inverse times A inverse times A inverse k times. So what we get is we get a wrapping of the circle around itself, either n times in this direction if n is positive, or n times or k times in this direction if it's negative. So the algebraic structure defines these interesting maps. All right, so we've talked about the line, and we've talked about the circle. So a natural question is, are there any other interesting one-dimensional examples before we move on to the two-dimensional case? Are there any other interesting one-dimensional topological spaces? What do you think? Can anybody think of some other ones that deserve to be included?
A line segment.
A line segment. So other one-dimensional objects, roughly. Okay, so a line segment might be a candidate. It's certainly one-dimensional in here, and on the boundary something a little bit odd is happening, but it's only happening sort of at some occasional points. A hyperbola, something like this. It's a one-dimensional object. Topologically, it's the same as two copies of a line. Okay, but that does, both of these are good ideas. So let's talk about them both separately. So the line segment generalizes a little bit more generally. We could think about not just a sort of a strange point with sort of half a dimension or something like that, but we could also think about maybe something like this. It's also more or less one-dimensional except for some odd points. And then it's not too much of a step to say, well, why don't we just consider arbitrary graphs? Graphs are examples of things which are, okay, more or less one-dimensional with nodes and edges. And we are going to be studying graphs in this course. So that's one kind of thing. Another sort of direction that we're going to be going is looking at this kind of situation where we have a space which is not connected. So the union of two lines, or maybe the union of two circles, that's also the same kind of idea. If you think of this as a space by itself, well, it's not connected, but perhaps it's still interesting. Right? So both of these are examples of spaces which are not connected, but for example, in the hyperbola, it's very natural to look at both branches at the same time. This idea of looking at spaces which are not necessarily connected leads to a theory called theory of links, which is a generalization of the theory of knots. So links are roughly knots with possibly more than one component.
What's a knot?
Oh, a knot is something like a trefoil knot that we talked about in our first lecture, where you get a rope and you string it around through itself and tie it up again. So let me give you an example of a famous link, which is not a knot. And okay, so don't copy this quite yet. Let me draw it first. Okay. So over there and under there, and then over here and under here. Okay, and this one goes under there and over here. And under there and over here. They alternate, all going over and under. Okay, so we have three circles like this. And can you see how they're overlapping? Okay. As we go around any one circle, we go over one, and then under one, and then over one, and then under one for all three circles. And these three circles, if you actually made a model of this, you would find that you can't separate them. They are linked. And maybe you can see it geometrically. The three circles are linked, but any two of them are not. So if I remove any one of those three circles, then the other two fall apart. That's a kind of interesting thing to get your head around. And this is a very famous thing called the Borromean rings. And so it's an example that it can be interesting to study links. Even when the constituents are relatively simple, the combination of them can be interesting. So those are some of the things that we'll make some contact with in the rest of the course. All right, so now we're going to move to two-dimensional surfaces. And we'll be saying quite a lot about this rather rich subject. And let's start off with the simplest example of a two-dimensional surface, which is the plane. The plane we can think of as A2, so I won't write R2. I'll say A2 instead, and we sometimes call it the affine plane. And we often draw it, to be specific, with coordinates. The coordinate system is rather arbitrary, but X and Y is natural, and the usual labeling. And if we want to, we can use this coordinate system to talk about any particular point in the plane in terms of its coordinates. So that point there might be 2 or 1. Its x coordinate and its y coordinate specified in an ordered pair. And this notation suggests to us that, in fact, A2 is really a combination of two A1s. And it is exactly equivalent to A1 cross A1, where this is a construction of topological spaces. This taking the product of two topological spaces. What it means is we're simply taking ordered pairs. Okay, this is an example of a product of spaces. And in general, what it means, if we just have x times y, and x and y are spaces, then by x and y we mean ordered pairs. Little x, little y, where little x belongs to, is from, say, x, and little y is from y. So it's a product of lines. And that's a very good way of thinking about it. But there's another kind of incarnation that the plane has. And to talk about that, I need to say a little bit more about what number system I'm using. So when I talk about a line, we've been calling it A1, and we're thinking about the coordinates 0, 1, 2, and so on. The natural question is, what are actually the entries of this line? And for us, most of the time we'll be thinking about rational numbers as being the basis for the continuum. So this is, most of the time, the rational number line. Now, my fellow mathematicians prefer to think about the real number line, but I have serious reservations about the real number line. I think there are very big logical difficulties. And with a rational number line, we stay with something which is very solid, which we can understand, and which actually corresponds to practical use in engineering, in computer science, in physics. Occasionally, we need to extend the rational numbers to get other kinds of irrational numbers included, and we'll allow ourselves to do that. So the rational number line is usually denoted Q. Okay? And so I'll use this notation, although I warn you that I think about Q perhaps not in the usual way. I don't think of this as an infinite set, but rather as specifying a type of mathematical object. And if you watch my Math Foundations series, then you'll know that I like to use RAT to stand for the rational type to represent essentially the same thing as the rational numbers. Okay, so now I bring this up because there's another way of thinking about the plane as another line. So the plane A2, which is now for us most of the time really the same as Q2, can also be thought of as a line. Can be thought of as a line over a bigger field, over the complex numbers. Where by complex numbers I mean complex numbers built up from rational numbers. So again, this is not the usual complex numbers that my fellow mathematicians like to talk about. It's something much more concrete. So for us, a complex number in this sense is something in the form a plus bi, where a and b are rational numbers. So now, this is also a field. This is a field, just as the rational numbers are a field. We can add, subtract, multiply, and divide these things, and we stay inside. Right? So it's a very nice field, very computationally concrete. And it's what actually you use in practice. I mean, an engineer actually is always using rational coordinates at the end of the day. All right, so now, but however, this complex number field is in some sense twice as big as the rationals. It's already planar in itself. And so we can think about what we've been calling A2 as being A2 over the rationals as being pretty well the same thing topologically as A1 over the complex numbers. Or to put it another way, a two-dimensional space over the rationals is the same as a one-dimensional space over these complex rational numbers. So this gives us another way of thinking about the plane. And it's a very important alternative way of thinking, that the plane can be thought of either as a pair of rational numbers or as a single complex number. And we'll see the importance of that as we carry on. But so I just want to flag that now. All right, now let's turn to the sphere. Which is the next most natural two-dimensional surface, perhaps. And we'll have a lot to say about the sphere. The sphere arises in practice in many different ways. In mathematics, the two-dimensional sphere. And so let's go through a couple of them and see how they connect. So the first manifestation is just as a Euclidean sphere. And that means that we're considering the equation x squared plus y squared plus z squared, let's say equals 1, in three-dimensional space. Okay, so here's our three-dimensional space with an x, a y, and a z coordinate. And centered at the origin is our sphere. So this is 1 unit in any direction. So it's centered at the origin. It has radius 1. So a natural question is that's the equation for this. Can we also describe the points lying on it? Can we parameterize this sphere in a nice way? Just like we parameterize the circle in the plane in a nice way. And the answer is yes, we can. And so let's do that. So we want to parameterize this sphere. So to parameterize it, what we're going to do is we're going to let's extend that there. We're going to look at the south pole. Let's use blue. So there's the south pole. Let's call it. Let's put it there. Say S, and it's got coordinates 0, 0, minus 1. 0, 0, minus 1 down there. And also the other thing that we're going to need is the equatorial plane. That's the plane when z equals 0 with the usual x, y coordinates. And what we're going to do is we're going to do something very much like what we did for the circle. We're going to take a point in this equatorial plane, namely point x, y, 0. It's in the plane. And then we're going to draw a line between that point and our south pole. And that line is going to intersect the sphere somewhere. So maybe it meets the sphere at that point there. And what we want to do is we want to calculate that point, and we're going to assign the label to that point will be x and y. We can use x and y as a coordinate for that point on the sphere. Okay. This process is called stereographic projection. In fact, there are two common forms of stereographic projection. This is one of them. The other one is where you put the reference plane at the North Pole. Okay? The difference between these two pictures is pretty marginal. It's just a factor of 2. As you can kind of convince yourself by similar triangles. But it'll be preferable for us for other things to think of the relevant plane as being the equatorial plane of this sphere. All right, so we want to make this calculation now. Let's call this point something so we can refer to it. So there's the point P. And we want to get this point here. Let's call it Q. So how do we find Q from S and P? Well, just identifying the picture. Here's S, here's P, and here's Q. S was the point 0, 0, minus 1. This is the point x, y, 0. And this point we don't know. But it lies on the sphere. Okay, so what I propose to do is I want to describe this line. So this line, the line SQ, is described in vector form by saying, well, we are starting at the point 0, 0, minus 1, and we're going any multiple t of the vector SP. What's the vector SP? So just the difference between these two coordinates. So we have to take x, y, 0 and subtract this one here. So that's vector x, y, 1. And I write my vectors with round brackets to let you know that that's a vector while this is a point. Okay? So if I take this point now and I add this vector to it, then I'm going to get the point x, y, t is still needs to be there. There's t, so we again have tx, ty, and the third coordinate, t times 1 minus 1, so t minus 1. That's our point That's going to be our point Q. But we have to choose T so that Q is actually on the sphere. So we need to choose T so that Q is on the sphere. In other words, so that Tx squared plus Ty squared plus T minus 1 squared equals 1. All right, that shouldn't be too hard to do. So what do we get when we write this out as a polynomial in T? There's a T squared here with coefficient x squared plus y squared. There's a T squared over here, so I'll just x squared plus y squared plus 1. And then there's a linear term here, minus 2t when we expand this. And a plus 1 and the plus 1 on the other side, they cancel, so we just get 0. It's a quadratic equation in T, and one of the solutions is T equals 0, because T is a factor. And that's no surprise, because that's just the point S, which is also on the sphere. So this factors as T times T x squared plus y squared plus 1 minus 2 equals 0.
No.
Yes?
What if you, instead of pushed your sphere, such as a hemisphere, up to the point such that it's sitting on 0 and at a center at 1, 0, 0, 1?
Yep.
Is that what that means?
That would make the derivation a little bit simpler.
Yeah.
That would make the derivation a little bit simpler. That's actually quite a good idea. But it's still not too bad this way, and corresponds to the usual way of thinking about it, but you're quite right. Okay, so we can now know what T is. So T now is going to be 2 over x squared plus y squared plus 1. And then we can immediately substitute into here, so we get our formula for Q. So Q is then, has 3 coordinates. The first one is 2x over x squared plus y squared plus, maybe I'll put the 1 first. 1 plus x squared plus y squared. In fact, maybe I'll move it down here so we can write it all down. So Q equals 2 times x all over 1 plus x squared plus y squared, comma. The same thing with a y. 2y over 1 plus x squared plus y squared in the bottom. And then t minus 1. So if we take this thing and so we subtract 1, well, then we're going to get 1 minus x squared minus y squared all over 1 plus x squared plus y squared. And we should compare this with our formula for the circle. Compare with, I remind you, that E of h, when we were parametrizing the circle, the formula that we got was 1 minus h squared over 1 plus h squared and 2h over 1 plus h squared. I didn't actually derive that, but you can kind of see that it's very similar to this. Except that now the z coordinate is sort of playing the role that the x coordinate was playing before. It's the way we've oriented things, to be looking upwards instead of looking to the right. All right, so this is an important formula. Let's put a box around it. It's giving us a parametrization of the sphere. So if you plug 2 rational numbers x and y into there, you're going to get a rational number on the sphere. And conversely, any rational number on rational point on the sphere is obtained in this fashion for some points x and y, which are rational numbers. Now this stereographic projection has a number of interesting properties if we think of it as a mapping from the plane to the sphere. So let's maybe draw or write something down. So let's say that P is a mapping from the plane, which is A2, to our sphere, which is S2. That's our name for the sphere. It's a two-dimensional sphere. And its P of the point xy is, well, exactly this formula that we had over there. A formula for our stereographic projection. So this is a map from the sphere, from the plane to the sphere. And it's almost a bijection. It's almost a bijection. It's not quite a bijection because the point at the South Pole doesn't get mapped to any point on the plane, or is not the image of any point on the plane. In some sense, S corresponds to an additional point at infinity on the plane. So corresponds, the point S, our South Pole, corresponds to a point at infinity. On the plane. All right, this stereographic projection map has very important properties. And these are excellent exercises for you aspiring math students to work out on your own if you're not familiar with them. Okay. So the properties are that, first of all, P sends lines and circles in the plane to circles on the sphere. So, in other words, there's our equatorial plane. It's the xy plane, the z equals 0 plane. There's our equator, and then there's the our sphere. Egg shape there, but and we're projecting from this point here. And what we're saying is that if you take any circle lying in the plane, and you project it up, you're going to get a cone. And that cone, it's a kind of an oblique cone, will intersect the sphere in actually a circle on the sphere. What do I mean by a circle on the sphere? I mean the intersection of the sphere with a plane. So a circle on C, on S2 is just the meet of S2 with a plane. So a circle is. And if you take a line in the plane and you project it up, well, then you're talking about a plane. The projection forms a plane. And that plane will cut the circle, also in a circle. But it's now a special circle. It's a circle that actually goes through the South Pole. So in this story, the lines on the plane, the lines on A2 match up with circles on S2 through our south pole S. So that's a very, very important property. The second property is that P is conformal. What does that mean? It means that it maintains angles, or better yet, it maintains spreads. Okay. So it preserves angles, or the rational geometry equivalent of angles, which are spreads. Of course, are much better, but you can think angles too. So what does this mean? Well, it means that if you have two little lines meeting at some angle or some spread, let's say it's an angle of theta there, okay, and you project these two lines, we don't really care about what happens otherwise. When you project onto the sphere, you're going to get two curved parts of circles. Okay? But those two curved circles are going to meet tangentially also at some angle. And we're claiming that that angle that these two circles meet is exactly the same angle that the original two lines meet. That's the conformal property of the stereographic projection. How about in the sense of the circles?
Points.
Okay, so well, if you have 3 points over here and they're collinear, that means that they lie on a line. All what you can say is that their image is going to be on the corresponding circle. But, yeah. So I guess the collinearity is somehow expressed in this relation, but what happens to lines? Lines go to circles. All right, this version of this map is very closely connected to another important sort of geometrical arena called inversive geometry. And the inversive plane. Very closely connected, so let me say it at the sort of the same segment here. So the inversive plane is another manifestation of the sphere. So inversive geometry in its standard form takes place in Euclidean geometry, and the idea is that if you have a circle, an arbitrary circle in the plane, then there's a notion of inversion in that circle. Okay. And what is this notion of inversion? Well, it's roughly it sends points inside to points outside and points outside to inside, but it's more precisely what you do is you start with the center and you say draw a line like this, and then if you have point x inside here, then its image will be the point x prime outside here, which has a particular property that these two lengths, let's call that center O. Okay. We want O of x, say the length between O and x times the length between O and x prime to be the radius of the circle squared. That's in terms of lengths. If you want it in terms of quadrances, you just square this relation. So that defines a mapping called, so x goes to x prime is inversion in the circle that we started with. Let's call it C. So we might call that I of C. That's the map. So it sends x to x prime, and it sends x prime to x. It's an involution in the sense that if you do it twice, you get back to where you started. Now, some properties of the inversion is very interesting and important geometrical property or transformation, and it obviously sort of leaves the circle itself fixed. Okay? C itself is fixed under I of C. And points inside go points outside, and the closer x gets to O, well, the further x prime gets. And in the limit, well, what happens to O? That's an interesting question. O will have to be sent infinitely far away. So we need an extra point at infinity to make this work. In other words, to give O somewhere to go. So we need to augment the plane. We need to augment the plane with an extra point, a single extra point, which we might as well call infinity. So there's an extra point at infinity, which is somewhere infinitely far out in any direction, and the inversion sends O to I. All right, so in my next lecture, we'll carry on with this. We'll talk more about inversive geometry, and then we'll talk about some other important manifestations of the sphere that connect with this and complex analysis. So we'll see you then.